Good evening, students. Today we'll be doing module number 3. It will be predictive analytics. Under that, we have a sub-module called neural networks. Previously, I think Lata ma'am has completed time series, logarithm, logical regression, simple regression, and as well she's also done on decision tree. So in continuation to that, I will be handling neural networks. So what basically neural network means? So before I go ahead with what it means, neural network is also referred as artificial neural network or ANN. The inventor of the first neurocomputer, Dr. Robert Hecht Nelson, defines a neural network as a computing system made up of a number of simple, highly interconnected processing elements. So which processes the information by their dynamic set state response to an external input. Now, if you look at the fundamental structure of ANN, the idea of artificial neural network is based on the belief that working of human brain by making the right connections can be imitated using silicon and wires, living neuron and dendrites. The human brain is composed of 86 million nerves, which are also referred to as neurons. Now they are connected to another 1,000 cells by axons. Now stimuli from an external environment or input from sensory organs are accepted by dendrites. These inputs create an electric impulse which quickly travels through the neural network. A neuron can then send the message to other neurons to handle the issues or does not send it forward. Now typically if you look at the next diagram, you will be seeing on the left hand side the dendrites which accepts the input and moves on for processing the input by axons using nerve impulses, and then it transforms into an information transfer which is depicted by a brown colored circle. Now the artificial neural network are composed of multiple nodes which imitate biological neurons of human brain. Now the neurons are connected by links and they interact with each other. The nodes can take input data and perform simple operations. Now on this particular data, the result of these operations is passed to other neurons. The output at each node is called its activation or the node value. Each link is associated with artificial neural network are capable of learning, which takes place by altering weight values. The diagram illustrates a simple ANN which consists of an input, hidden and output. We will see a video to understand this, and the video is quite very simple to understand, and then we will continue further with the applications of the artificial neural network in different areas of business today.
And it goes like this. You have a roommate, which is the perfect roommate. And why is he the perfect roommate? Because he cooks every meal. And he cooks 3 types of foods. Apple pie, a burger, and chicken bone. And he has a rule for what he cooks. So he first looks outside at the weather. And it can be sunny or it can be rainy. And if it's sunny, he cooks apple pie because he's happy. And if it's rainy, he cooks a burger. So this scenario can be easily modeled by a very simple neural network. If you don't know what a neural network is, I recommend you this other video that I have on the channel. It's called A Friendly Introduction to Deep Learning and Neural Networks. You should check it out, and that'll give you an idea of what neural networks are. So this would be a very simple neural network. Neural network has an input and an output. And so in this case, the input is, for example, a sunny day, and the output is an apple pie. Or if the input is a rainy day, then the output is a burger. So let's do some math, and for math we're going to use vectors. So we're going to represent the food by some vectors and the weather by some other vectors. 0 vector, and the rain day is going to be represented by a 0, 1 vector. And so what the neural network does is, if it receives a 1, 0 vector corresponding to a sunny day, it returns a 1, 0, 0 vector, which is an apple pie. And if it receives a 0, 1 vector corresponding to a rainy day, it returns a 0, 1, 0 vector, which is a vector corresponding to a burger. And this neural network is actually just a very simple matrix. So this matrix works like this. And if you're not familiar with, or if you need to brush up on matrix multiplication, there's a lot of videos that I recommend. In particular, Khan Academy has some pretty good videos. But this is how it works. I take my matrix and I multiply by the vector 1, 0 corresponding to a sunny day. My result is the vector 1, 0, 0 corresponding to an apple pie. And if I take the vector 0, 1 corresponding to a rainy day, the answer is the vector 0, 1, 0 corresponding to a burger. So this neural network is just a linear map that sends the sunny day to an apple pie and the rainy day to a burger. If you're used to seeing neural networks not as a matrix, but as a bunch of nodes with arrows, this is it. This is the matrix on the left is turned into the arrows on the right. As you can see, the dark arrows are labeled 1 for the ones in the matrix, and the light arrows are labeled 0. And how it works is that if you take the vector, for example, corresponding to a sunny day, which is 1, 0, then this vector goes inside the first layer of nodes, and then the value of the node is multiplied by each of the edges and then added in the right. So this becomes this vector 1, 0, 0. You can check that, and that's actually equivalent to matrix multiplication. And that's why neural networks are really representing a bunch of matrix multiplications. And so here you get the vector 1, 0, 0, which is the vector corresponding to an apple pie. And you can check that if you input the vector corresponding to a rainy day, which is 0, 1, you're going to get 0, 1, 0, which is corresponding to a burger. Okay, so that was a simple neural network. Now let's go to a slightly more complicated problem. Let's say we still have the...
Okay, you would have seen the first simple thing where it speaks about the matrices here. So when you're applying 1, 0 on a sunny day, and you have 1, 0, 0, which is a matrix, the first row you see 1, 0, 0 there. First column you see 1, 0, 0. In the second column, when you apply the rainy season, it becomes 0, 1 on the column, and then on the matrix, you see 0, 1, 0 on the second column there. So now when you apply it, that is where you see the difference there. In the previous slide probably you would have understood that how an apple pie, when you multiply, it's nothing but a multiplication of matrices which we are using here. So further to continue, just observe this and we'll come back again and redo you can always redo this video and try to understand how it works. They're very simple matrices. Okay, enjoy watching it, and we'll get back again as quickly as possible as soon as the video is over.
Perfect roommate still cooks every day, but now he doesn't base his cooking on the weather. He's actually very organized and very methodical, and he just cooks in sequence. So one day if he cooks an apple pie, then the next day he cooks a burger, and then the next day he cooks a chicken, and then the next day again apple pie, and then burger, and then chicken, and then so on and so on. So we can always tell what he's going to cook based on what he cooked the day before. For example is if on Monday he cooks an apple pie, then on Tuesday he cooks a burger, and on Wednesday he cooks a chicken, then on Thursday an apple pie, then on Friday a burger, then on Saturday a chicken, and so on and so forth. So this is not a normal neural network anymore. Now it's called a recurrent neural network, because now, well, in this case there's no input for the weather, so the bottom arrow doesn't come from anywhere, but the output goes back in as input. So this apple pie over here, if you did an apple pie yesterday, then this comes back as input, and then the output is a burger. So after today you'll cook a burger. And if today he'll cook a burger, comes back as input, chicken is the output, means tomorrow he will cook a chicken, and so on. And we input the chicken, etc. So the neural network really looks like this. The input is the same output that came out from the previous one. So let's recall that these are the vectors for the food, which are 1, 0, 0 for apple pie, 0, 0 for the burger, and 0, 0, 1 for the chicken. And let's make a neural network that will do the job, and the neural network is going to be this matrix. Also very, very simple matrix. Because what this matrix does is the following. If we multiply, for example, by the vector of the apple pie, take a look, we're going to get this vector, which is the vector corresponding to a burger. You multiply the matrix by the vector of the burger, you get the vector of the chicken. And finally, if we multiply the matrix by the vector of the chicken, we get back the vector of the apple pie. So this neural network is simply a linear map that takes the apple pie and maps it to the burger maps it to the chicken, and the chicken maps it to the apple pie. And it's simply this matrix. But as before, if you like neural networks more as a diagram with nodes and edges than as a matrix, this is how it looks. And the way it looks is following. I have, for example, my vector corresponding to the apple pie. These entries in the vector go here. And now I haven't drawn all the edges, but I've only drawn edges that have label 1. And the edges with label 0 are just not drawn. So this matrix multiplication is exactly doing this. And now we get the vector corresponding to a burger. And you can always check that if you put in the vector burger, you get chicken. With the chicken, you get back the apple pie. So this is how the neural network looks. But now let's take a look. The three nodes on the right are the output, and they're food. But the output comes back in as the input. So really, this is how the neural network should look, right? The three entries of vector corresponding to the output goes back and leads to the input. And so that's why it's called recurrent, because the input is not just one thing. That input comes from the output. So that's it. That's a very simple recurrent neural network. So let's look at a more complicated one. Let's go back to the perfect roommate situation. And now, this rule for cooking is going to be a combination of the two previous rules. So it's still very methodical, and he still cooks in sequence: apple pie, burger, chicken. But his decision of what to cook is going to depend on the weather as follows. If it's sunny, he's going to go outside and enjoy the day, and he's not going to be cooking, so he's just going to give us the same thing as yesterday, leftovers. And if it's rainy, then he stays outside, he has nothing to do, so he cooks the next dish on the list. So if it's sunny, we get the same thing as yesterday. If it's rainy, we get the next thing on the sequence. So here's an example. Let's say on Monday it's an apple pie. And so on Tuesday we check the weather and it's sunny. And if it's sunny, then he doesn't cook anything new, so we get an apple pie. I hope it's not a confusion that I put the sunny weather for Tuesday under Monday. Yes, just for diagram purposes. So on Wednesday he checks the weather. If it's rainy, then he stays home and makes something different. So a burger is the next thing on the list. And if on Thursday it's rainy, then again he makes chicken because he stayed home and cooked the next meal. And if Friday is sunny, then he goes outside, doesn't cook anything new, so on Friday we get chicken again. And if on Saturday it's rainy, he cooks the next dish, which is an apple pie. And if Sunday is sunny, then he cooks an apple pie again, and so on and so forth. So this is how this recurrent neural network looks. Now there's an input coming from underneath, which is the weather, and an output that is the food that comes back as input. So check this out. Yesterday's food was apple pie, and today the weather is rainy. Then these two things feed into the neural network, and the output is a burger, because in a rainy day you cook the next food, it's a burger. So again, let's look at the vectors. So recall that apple pie is vector 1, 0, 0, burger is 0, 0, chicken is 0, 0, 1, and 1, 0 for sun A and 0, 1 for brain B. So I'm going to show you the neural network not as a matrix because now it's more layers, but as a bunch of matrices and some maps. So here are the two matrices. One is called the food matrix and the other one is the weather matrix. And then we add them and then we merge them on a kind of non-linear operation. I'm going to show you all these steps one by one. So let's start by the food matrix. So this is how the food matrix works. As you can see, it's a 3 by 6 matrix, but I've kind of artificially cut it into two 3 by 3 matrices, so it looks like a concatenation of them. And if I multiply the matrix by the vector representing an apple pie, so this is what I get. I get a concatenation of two vectors where the top vector is the same thing that came in, because as you can see, the top 3 rows of the matrix are the identity matrix. And the bottom 3 rows of the matrix are the food for the next day, so the burger. For redundancy, let's look at another example. If I multiply this matrix by the burger vector, I get this, which is the vector, concatenation vector of the burger, which is the food for the same day, and the food for the next day, which is the chicken. And finally, if I multiply the matrix by the vector corresponding to the chicken, I get the vector concatenation of the vector corresponding to the chicken, which is the food for the same day, and the apple pie, which is the food for the next day. So what the food matrix does, all it really does, is it takes your vector for today's food, and it returns the vector for today's food and the vector for tomorrow's food concatenated. That's all it does. Now let's look at the weather matrix. So the weather matrix is also a concatenation of matrix, and of matrices, where the top matrix just has 3 ones on the first row, and the bottom matrix has 3 ones on the second row. Check out what this does. If I take the weather matrix and multiply it by the vector corresponding to a sunny day, then I get 3 ones on the top and 3 zeros on the bottom. So I get basically a vector that tells me that it's the same day. Because there's ones in the same day and zeros on the next day. If I take and multiply it by the matrix by the vector corresponding to a rainy day, I get zeros on top for the same day and ones on the bottom for the next day. So this weather vector is kind of telling me, should I cook today's food or should I cook tomorrow's food based on the input. And so now some magic happens. We add these two and we should get a clear signal of what we should cook the next day based on what's the food for today, what's the food for tomorrow, and should we cook the food for today or should we cook the food for tomorrow. So this will be much more clear in an example. So the example is yesterday we cooked an apple pie and today the weather drink. So here is the result of when we multiply the food apple pie vector by the food matrix. So we get the food for today and the food for tomorrow. This is the result of multiplying the weather matrix of rainy day by the weather matrix. So it tells us a signal of we should add the next day part of the vector. And if we add this 2, we get this vector. And notice that the largest entry here is the 2, and the 2 hints of a burger because the vector for a burger has 0, 1, 0. So that we're going to try to extract that 2. And for extracting the 2, we use the merge map. But notice that this is very special. The first part, the first summon, tells you what's the food for today and what's the food for tomorrow. And the second summon kind of tells you which one to pick. If you go for the same day, or you go for next day. So those two decisions together form the decision of what to cook the next day. And so just to wrap this up and put these two together into the burger vector, I'm going to now show you the merge map. The merge map, what it does is, well, first of all, it uses a nonlinear function that turns this vector into this vector. So it basically takes the largest entry and turns it into a 1, and all the other entries and turns them into a 0. If you experience with neural networks, you can think of nonlinear map as a one-hot encoding, or as a combination of a linear map and a signal. But that's not important right now. And then what we do, what the merge map does, is it takes these vector formed by the top three entries and the vector formed by the bottom three entries, and just adds them. And we get the result is the vector 0, 1, 0, and that is the vector corresponding to a burger. And that's the answer. If I take an apple pie and a rainy day, I get a burger. If you like to see this arrow, this merge map as a matrix, you can see if I multiply this matrix by the concatenation of two vectors, I get the sum of them. And again, if you like to see neural networks not as matrices and maps, but as additional edges and nodes view, this is how it goes. So we've got a food section, a weather section, an add section, a nonlinear section, and a merge section. And it goes as follows. If I input my vector for the apple pie and my vector for the main game, the vectors go into the nodes like this. And the matrix multiplication, as you can see here, I have edges that are labeled 1 are drawn, and the edges that are labeled 0 are not drawn. And the matrix multiplication is exactly putting the values through the edges and multiplying by the weight of the edge and adding them. So I get this for my results of my matrix multiplications with the food matrix and the weather matrix. And then I add them, and addition is given by just adding this to the arrows, so I get this. Then I apply my linear function that takes the highest entry and turns into 1 and everything else into a 0. And I get this. And then my last matrix, which takes the vector and adds the top three entries and the bottom three entries, gives me this. And boom, I get the vector corresponding to a burger. So that's how the neural network looks. Now, the word recurrent or there. Notice that these three nodes correspond to the food coming in, and these three nodes correspond to the food coming out. So really what happens is that the output or the food coming out feeds back into the neural network as input. So really this is how the neural network looks. This vector of my 3 goes back into the neural network and feeds in as input. That's why it's called recurrent neural networks. And recurrent neural networks are super useful in many ways. In particular, they're very useful when your data is sequential. So whenever your data looks like it forms a sequence, and whenever the next data point depends a lot on the previous ones, then recurrent neural networks are good. An example of this would be stock prediction, right? Because stock prediction, the price for the stock per day depends a lot on the price yesterday and the price 2 days ago. It's a sequence generation, so anywhere where your data follows sequence like text generation, you're trying to guess the next word in a sentence, like when you're typing in your phone and the phone guesses the next word, that depends a lot on the previous word and on the word before. Or even for letters, you're trying to guess the next letter, that depends a lot on the letter that just happened. So things like voice recognition is used when you're trying to guess a string of words. Then you have the sound coming in, but you also have the previous words. So you have 2 places where your information comes in order to guess the next word that you said. So that helps give an idea of how important recurrent neural networks are. But now the next question is how to train a recurrent neural network. And I won't get too deep into this, but it's the idea is something like this. Our neural network really depends only on these parameters, right? These are the right weights that make our model great. And the way you train them is to start with some random weights. So imagine if A, B, C, D, E, F, and all the way to capital are just random numbers, and train them using gradient descent. So if you want to brush up on gradient descent, or if you haven't seen it, I recommend the video that's on my channel called an Introduction to Learning Neural Network. What it does is you have some parameters and you have an error given by your data. So you fit in your data to your neural network and it gives you a big error, and you do steps to reduce these error loads. So the error is represented by a mountain called Mount Error, and you descend this mountain in order to reduce the error. Of course, for recurrent neural networks, it's not going to be the same error function, so it's not mount errors. Now it's mount Tillman's error. That's going to be a new error function, and sending from the mountain is equivalent of using that error. So that's all, folks. I hope you enjoyed this video as much as I enjoyed making it. If you liked it, please subscribe. Please hit like or share it. And feel free to comment if you have any questions. I love reading your comments. I try to respond to most of them. And if you have suggestions for what the next video you'd like to see, or applications, or in general want to chat about machine learning, feel free to throw in a comment. These are my coordinates, my LinkedIn, my...
Okay, now we saw the video. So it's a very simple video, and once you watch this, it would be quite easy for you all to understand how the matrices work. It's an application of linear and non-linear networks there. So if you have, just go through the video again, maybe if you have not understood during this, and if you have any doubt, please come back to me. I will be able to help you out with. I think this particular video is also useful for non-mathematics students background also. It's very simple, and you should be able to ace it. Now next, let's see the types of artificial neural networks. There is something known as the feed-forward artificial neural network. In this, the information flow is unidirectional. There is no feedback loop, and unit sends information to the other unit from which it does receive any information. There are no feedback loops, as I said earlier. They are used in a pattern generation, recognition, and classification. They also have fixed inputs and outputs. The types of artificial neural network: feedback ANN. Feedback loops are allowed. If you see the concentric circles there, they're used in content addressable memories. Now let's look at three aspects of machine learning. One is the supervised learning, unsupervised learning, and reinforcement learning. Each arrow represents a connection between two neurons and indicates the path for the flow of information. Now each connection has a weight, an integer number that controls the signal between the two neurons. If the network generates a good or desired output, there is no need to adjust the weight. However, if the network generates a very poor result, or a poor or undesired output, an error, the system alters the weight in order to improve the subsequent results. Now ANN are capable of learning, and they need to be trained. There are several learning strategies, as I said earlier: supervised learning, unsupervised, and reinforced learning. In supervised learning, it allows the teacher, that is a scholar, than the ANN itself. For example, the teacher feeds some example data about which the teacher already knows the answer. Now, for example, pattern recognizing. The artificial neural network comes up with the guesses while recognizing. Then the answer provides, then the teacher provides the ANN with the answer. The network then compares its guesses with the teacher's correct answer and adjustments according to errors. Please note the word correct is in quotes, so that's a key word. You have to understand that and see how supervised learning works. Now let's see the unsupervised learning. It is required when there is no example of data sets with no answers. For example, searching for a hidden pattern. In this case, clustering, that is dividing a set of elements into groups, a cluster into groups, subgroups, and according to some unknown pattern is carried out based on the existing data sets present. Now in a reinforced learning, the strategy is built on observations. It's all complete in observation. Now the ANN, the artificial neural network, makes a decision by observing these environments or its environment. If the observation is negative, the network adjusts its weight to be able to make a different required decision the next time. Now let's look at the application of the artificial neural network. It is used in aerospace industry, where it is used in autopilot aircraft, unmanned air surveillance aircrafts, in aircraft fault detections, in MRO. MRO is nothing but maintenance, repair, and overall. So these are the areas where defense is a major area which uses this because to protect the country's intellectual property or to protect the country's citizen. So this is all used to ensure the enemies don't attack. BrahMos, if you see the BrahMos, right? Such a beautiful image of BrahMos, which is seen here. If you look at it, even Abdul Kalam had also worked on Agni and BrahMos missile, and this is a fantastic weapon which they had done it so that the enemies don't target us. Now let's look at the anomaly detection. If you look at the diagram there, it's an artificial neural networks are experts at recognizing patterns. They can be trained to generate an output when something unusual occurs that misfits the pattern. For example, if you look at a tsunami, it's or a weather condition. Anomaly detections can predict the weather conditions, and it can help the fishermen to stay away from the sea or the high tides. Right? Now let's look at the third one. If you look at the third one, if you look at the parking lot, there are red lights there. These are lights where the cars have occupied the parking lots. Now if it turns green, it means the parking lot is open and anyone who is looking at it can come and park it over there. So these are done through automobile guidance systems there. So which guides you, and it works basically on sensors and neural networks there. All the major malls in India use parking lot guidance surveillance systems. Okay. Now let's look at the control. The artificial neural network are often used to make steering decisions on physical vehicles. Now typically when I talk about physical vehicles, we are referring to for example, let's take an example of a Google car or a Tesla car, which is guided through the traffic management, and it applies sensors to take proper decision whether to take a longer route or a shorter route. Even in Bangalore, if you see, or any major cities you see, it gives you conditions on GPS. It says, okay, today don't travel towards MG Road, the traffic is very high, please use an alternative route, use the Cubbon Road to reach the inner pockets of Falsoor, right? If you're using an MG Road now, maybe the traffic jam is too high and it might take a while to get into Falsoor. So use a Cubbon Road to reach Falsoor. So this is just an example I'm giving. The next one is military. Okay, now weapon orientation and steering and target tracking, object discrimination, facial recognition, single image identification. So this is so very critical in military because when enemies are targeting and coming and entering into India, the facial recognition helps them to ensure that these guys are avoided and these guys are arrested immediately so that they cannot target the country. So and also it is also used in other areas, targeting and tracking. So to track where are the militants' movements in Jammu and Kashmir, for example, and how to target their hubs so that the country can be protected. And if you look at today's cell phone as well, if you are stealing a cell phone, it has facial recognitions. Now when you open a cell phone, when you put in your fingerprint, and then if you see a camera popping up. Now let's say the same thing. If somebody else is putting a fingerprint, it doesn't open up. You try to do something, even the camera doesn't work and it doesn't open up. So that's nothing but it never recognizes your face and it will never try to show up or it will not open up. Right? The next one is the electronic. The code sequence predictions, the IC chipsets layout, the chip failure analysis, machine vision, and voice synthesis. All these areas where the chip manufacturing, it goes into the VLSI design. We call the VLSI. It's a very large semiconductor industry where it goes into a chip level component manufacturing where they use soldering and ensures all the chipsets are all embedded into the systems, right? So this is just an example we're looking at. Now let's look at further. The financials, in the financial industry, the real estate appraisal or the loan advisor, the mortgage screening, corporate bond rating, and all these examples like credit application evaluator, document reader, current valuation, all these areas where artificial intelligence takes random access into it and tries to put in sensors, identifies the purchase pattern of a particular person, the type of loans a person is picking up, and based on that it ensures whether the loan can be approved or it can be disapproved. Even credit card applications today there are evaluators where it is run through an artificial neural network again. Now if you look at the industrial industrial manufacturing process control, the product design and analysis, quality inspection systems, the welding quality analysis, and all these areas, the paper quality predictions, chemical product design analysis, dynamic modeling of chemical process systems, machine maintenance, and project bidding and planning environment. All these are part of your industrial application of neural networks there. In every area, if you take about any designing, let's say you design a component. Today, if you look at it, the 3D printing has become very popular. So if you show a particular two-dimensional object, it will immediately capture that and show you the different angles how that could be converted into three-dimensional object, right? So that is an advancement. The 3D designing is again very popular in the industrial side of it when it works on components now. When you look at the third one, the medical side of it. In the medical, this is used. Artificial neural network is used in carrier cell analysis, EEG and ECG analysis, prosthetic design, and transparent time optimizer. Now the speech. Speech level, if you look at the cell phones, the old cell phones, if you, for example, Siri, or you talk about the Google Assistant, right? So what happens? There's a speech recognition. So when you record your voice, it recognizes your voice and tries to translate it into its language and try to find out. So let's say you are asking for a restaurant in Matike, a restaurant in New Bell Road. So it recognizes and it says, excuse me, are you looking for a restaurant in New Bell Road? I couldn't get it. So again you need to repeat it. So all these are based on speech recognitions and text to speech. This is a very old technology. In fact, Samsung was the first company which started with the speech recognition way back, voice recognition. It was called voice recognition way back in 1999 and 2000. When the Samsung launched its unique features in the Samsung phones and became very popular. Now the second thing, the next one is the software. The pattern recognition in facial recognition, optical character recognition, all these are part of the software side of it. Then the signal processing, neural networks can be trained to process an audio signal and filter it appropriately in the hearing aids. Now the telecommunication side of it, image and data compressions, automated information services, real-time spoken language, translations, all these are part of the telecommunication network there. Now coming into transportation, truck brake system diagnosis, your vehicle scheduling, routing systems, you need to route which area the truck has to go, is there a particular fashion where the truck has to follow. For example, FedEx like stuff or Blue Dart, they will have a certain route through which it has to pass through those routes to pick up every product, load it to the truck and move on. So they cannot deviate that route. So route planning is again very important there. Then balancing, vehicle scheduling, how it should be scheduled every 2 hours or 3 hours based upon the number of load factor, based on the infrastructure, the braking systems, diagnosis, everything all together would be taken care of. The next one is the time series prediction. I think Lata ma'am would have taken time series there. Now again, artificial neural network are used to make predictions on stocks and natural calamities as well. Now let's look at the Rosenblatt perception. The Rosenblatt perception is a neural network compound of a single artificial neuron. Now this artificial neural model is the basis of today's context neural network and was until the mid-80s state of art in artificial neural network. Now the Rosenblatt perceptron model is a binary single neural model. The input integration is implemented through the addition of weights input that are fixed weight are obtained during the training stage. If the result of this addition is larger than the given threshold theta, the neuron fires. When the neuron fires, the output is set to 1. Now otherwise it is set to 0. The equation can be rewritten as the following. If you look at this, on the left hand side you have x1, x2, x3, x4, x5, right? Now similarly you have in the circles the nodes w1, w2, w3, w4 and w5, which are all mapped on to sigma and then to a symbol called tilde or s, right? Now h of x, when you apply h of x equals 1, 0, and that is if w to the power of t into x is greater than equal to 0, or if you apply 0 if w to the power of t dot x is less than 0. Now if you apply this here, h of x equals 1, 0, or if w1 x1 plus w2, it is a series. W2, W3, W3, X3, W4, X4 and so on till WD dot XD, which is greater than or equal to theta. Now when you apply 0 here, again you apply the series there, which is again less than 0. Now this particular equation can be rewritten, including when it is known as the bias term is X0 XO equals 1 or WO equals theta. Now H of X equals 1 if WO, XO, W1, W2, W3, W2, X2, W3, X3 and so on till W3 and XT, which is greater than or equal to 0. Now similarly, if I apply 0 there, WO dot XO plus W1 X1 and so on till W3 X3 is less than 0, right? Now this model implements the functioning of a single neuron that can solve linear classification problems through very simple learning algorithms. Now Rosenblatt Perceptron are considered as a first generation of neural network. This simple neuron network model has main limitations of not being able to solve non-linear separable problems. Now confusion matrix. A confusion matrix is a table that is often used to describe the performance of a classification model or a classifier or a set of data sets, data or a set of test data for which the true values are known. The confusion matrix itself is relatively simple to understand, but the related terminologies can be confusing. Let's start with an example confusion matrix for binary classification. Now n equals 165. N is nothing but a number. Now actual no, actual yes. This is on the first column, and predicted no, predicted yes. Now actual no said predicted no said 50, predicted yes said 10. Now actual yes is 5. Now predicted yes is 100. Now what does it mean? There are two possible predicted values, yes or no, right? That's what we saw here, yes or no. Now if you are predicting the presence of a disease, for example, yes would mean that they have the disease, and no would mean they did not have the disease. The classifier made a total of 165 perceptrons, 165 predictions. That is example, 165 patients were tested for a presence of that disease. Now out of these 165, the classifier predicted yes for 100 and 110 and times no for 55 times. Now in reality, 105 patients in the sample has the disease and 60 patients do not have. If you look at this, if you look at that row, actual no, actual says no there. So that 50 plus 10 equals 60, right? Now actual S is 5 plus 105, which is 105. That's what exactly it is shown here. Now if you look at, let's now define the most basic term, which are whole numbers, not rates. True positive is represented by TP. These are cases in which we predicted S, they have a disease and they do not have the disease, and they do have a disease, right? The two negatives, we predicted no and they don't have the disease. False positive, which is represented by FP, we predicted yes but they do not actually have the disease. Also it's called as type 1 error or hypothesis actually. The false negative, which is Fn, we predicted no but actually do have a disease, also known as type 2 error. So when these terms are added to the confusion matrix and also added to the rows and columns, what exactly happens? Let's see. Now 165 patients, actual no, yes is no. Now under predicted no, predicted yes, we see total negative is 50 and your false positive is 10, right? Now if you look at false negative is 5, total positive equals 100. So if you look at on the right hand side, you see 60 and 150, we already know. Now when you look at this column, 50 and 5 is 55, 10 and 110 is 10 and 100 is 110, right? So this is the list of rates that are often computed for a confusion matrix for a binary classifier. Accuracy. Overall, how often is the classifier correct? Now the total positive plus total negative divided by 100. 100 total positive plus total negative is 50 divided by 165 patients is equal to 0.91. Misclassification rate, how often it is wrong. The false positive plus false negative divided by total. False positive is 10 and false negative is 5 divided by 165, which gives you 0.09, which is equivalent to 1 minus the accuracy, which is known as the error rate. The true positive rate, when it is actually S, how often it predicts S. Now the true positive actually S is equal to 100 positive cases divided by 105, which is equal to 0.95, also known as sensitive or recall. Now false positive rates, when it is actually no, but it's actually no. How often it predicts yes. The false positive by actual numbers. The false positive is 10 and divided by 60, which is your actuals, right? Actual number. The total negative rate, when it is actually no, how often it predicts no. The total negative by actual number. The total negative is 50, where the actual number is 60, right? Which gives you 0.83 equivalent to 1. The positive rate is also known as specificity. Please, I hope this diagram is very useful for you all to understand how the calculation works. The precision here, when it predicts S, how often it is correct. The true positives, the true positive divided by predicted S. Now true positive is 100 and divided by 110, which is a predicted number, which gives you 0.01. Now let's look at the prevalence. How often this S condition actually occurs in our sample? Actually S says 105, but the total is 165, which is equal to 0.064. 105 comes on the actual S there, divided by you have 165 is the total number of patients, which is 0.64. A couple of terms you should remember, which is worth noting. The null error rate. This is how often you could be wrong if you always predicted the majority values. In our example, the null error rate would be 60 by 165. What is that 60? 60 is nothing but your actual number divided by 165 patients, which is 0.36. Because if you always predicted yes, you would always go wrong for the 60 no cases. Right? Only be 60 there. This can be useful baseline metrics to compare your classifier against. However, the best classifier for a particular application will sometimes have a higher error rate than the null rate, as demonstrated by the accuracy paradox. The Cohen kappa. This is essentially a measure of how well the classifier performed as compared to how well it was performed simply by chance. In other words, a model will have a high kappa score if there is a big difference between accuracy and the null error rate. Now the F score, this is a weighted average of the true positive rate, record and precisions. Now ROC curve, this is commonly used graph that summarizes the performance of classifier over all thresholds. It is again generated by plotting the true positive rate, y-axis, against the false positive rate, which is an x-axis, as you vary the threshold for assigning observations to a given class. Now let's look at tactical planning. As defined by Norris, it consists of short-term or intermediate-term regular planning and budgeting activities dealing with administrative and operational activities that unfold with the overall strategic context of the objective established by strategic planning. While strategic planning focuses on identifying broader statements of institution focus in specific area, tactical planning serves three major functional purposes. First, it helps each division and area to identify and commit to a way it can serve the university mission, vision and strategic purpose. Why are we using university here? It is just an example I've taken from the university. It can be applied to any industry, right? It also identifies the key priorities of the individual division or the areas, the statement which determines the nature of division or area and its relationship with those it serves. Now again, it establishes particular goals necessary to meeting these needs successfully. Third, tactical planning identifies clear and specific objectives for fulfilling the goals of the organization, activities that are which have measurable results, or you call key result areas, the key results there, the performance area. Now, if you look at this, tactical planning allows divisional area to prioritize the needs and activities over a 3-period time. We have taken a 3-year period levels here. So, ensuring that the annual operations consider what relationship exists between decision activities made in 1 year and the future goals and events. Though the scope of the plan covers 3 years, the plan should be reviewed annually to ensure the progress is being made and monitored, that goals and activities remain relevant to the division or administrative area. Changing the needs and the plan takes place, or a very or a plan, right? So administrative area changing needs, and that the plan is actively supporting the organizational strategic plan. Now, tactical planning is not meant for burden divisional areas with additional work, but rather to organize thinking and planning that often takes place on a less centralized basis. Now, making planning a proactive rather than the reactive activity, it emphasizes forward thinking in everyday activities and provides divisions and areas and touchstone to mark their progress. At level 1, if you see a strategic 5-year cycle, at level 2 it is a 3-year cycle, level 3 it's an annual cycle. So it goes by that. Universal missions and goals becomes the first level 3. Academics and administrative program unit plan comes into level 3. Now a 3-year period, again mission and goals are reviewed. Under divisional areas you have academic affairs, placements, finance, information, mission and ministries, student affairs, you have enrollment management, civic management, human resources, managing and marketing, alumni. So this is a longer cycle. Now when you look at the level 1 university mission, again redoing it, then you build a vision statement, you have a strategic plan on it, right? Now apart from that, it also goes into an external analysis, SWOT analysis and internal analysis, which is a self-study there. So it's a very longer cycle. So if you look at it, you look at the arrow marks, how it is passing. If you look at level 3 and level 2 and level 3, the divisional and area plan and academic and administrative plan is a two-way network there. Now if you look at other areas, it's all one-way network, right? So this is what is tactical planning. I think with this we'll be closing artificial neural network, and if you have any doubts you can always come back to me and I'll be readily available to help you out. Thank you students, enjoy your evening.